Section 22 of The Science History of the Universe, Volume 3. This is the LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 5. The Development of Power Transmission. The location of a convenient spot for the economical generation of electric power usually does not coincide with the center of its consumption, so that the connection of these 2 points presents a problem which has consumed the energies of many engineers. Among the natural available sources of energy today, which are most prominent, are coal and liquid fuels and the fall of water. Coal and the liquid fuels can, without much expense, be brought to many industrial centers, and the power plant is then erected at these points. In many cases, however, as in the western part of this country, the cost of cartage is prohibitive. On the other hand, water powers are abundant, but are not usually found at points where manufacturing may with profit be carried on. The power available in such waterfalls, and which has been wasted for centuries, is at last being utilized through the medium of electrical transmission and has become an immense addition to the sources of energy. With the enormous amounts of power now required, the natural resources of fuel are fast becoming exhausted, and America would soon be left without the means of carrying on civilization, had not methods of distributing the inexhaustible supply of energy in waterfalls been developed. The importance of the work which has been done and is still being done by those engaged in the design of these power lines is appreciated by few. Some of the essential parts of such a system of power distribution need consideration. The powerhouse must be located on a stream which has at all times a sufficient flow to operate the generators at their full capacity. Failing in this, an artificial lake or storage reservoir may be constructed so that the maximum and minimum flows may be more nearly equalized. In order that the power may be economically transmitted, the voltage of the line must be high, and the higher the better. The loss in the line varies as the square of the voltage, so that with the same line loss, the power may be transmitted 4 times as far by doubling the voltage. It will therefore be seen that the voltage is one of the important factors in determining how far power shall be transmitted. There is a limit to the voltage which a generator may develop on account of its manner of construction, and at present this seems to be about 13,000 volts, although machines of higher voltage have been built. The next important factor is the transformer, and in the perfecting of this piece of apparatus, a great deal of attention has been centered. By its means, the voltage may be raised to almost any degree with a very slight loss in power, the limit being the ability of its insulating materials to resist breakdown. In the last 15 years, the advance in the art of constructing transformers has been such that they may now be built with the same assurance for 100,000 volts as they were then for 3,000 volts. There is, moreover, prospect of their successful operation at 500,000 volts. Why, then, are lines not yet operating at 500,000 volts? Now comes the weakest spot of the system, viz., the insulation of the line. The development of insulating materials has not been able to keep pace with that of the means for producing high voltages, although it has been rapid. Insulators for carrying the lines have increased in size and cost until they have assumed great importance. Wooden poles have been replaced by steel towers, and rights-of-way have been granted, through which the lines may pass. They are regularly patrolled by men whose business it is to report to the power station immediately any defects observed. Operation of these lines in actual practice has not been as difficult as laboratory experiments tended to prove. There has been less leakage from the line than was expected, and also fewer breakdowns. One of the main difficulties in the operation of these long lines has been due to lightning discharges, but even these are fast becoming eliminated. New lines are usually troubled with malicious persons who delight in shooting off the insulators, but these have been cured by the severe punishments inflicted. Large birds have sometimes caused arcs to start between the line wires by approaching too close. Each year sees the limit of successful operating voltage raised. What would have been considered impossible a few years ago is now an accomplished fact. In 1908, the highest operating voltage was 110,000 on a line in Michigan about 100 miles in length. 60,000 is now a standard voltage. To what distances power may be transmitted in the future we may only surmise, but it seems assured that all parts of the world will ultimately be traversed by these power lines. In reviewing the history of the development of power transmission, an idea of its rapidity may be gained by observing the work of the pioneer plants. Although much of the work was done in Europe, America has accomplished her share and has developed the alternating current system of power distribution to the point where it has finally triumphed over the European direct current system. During the years from 1880 to 1890, power transmission was affected almost entirely by direct current. Electricity for power and lighting was sent out over the same lines, and the power load usually consisted of a number of small motors. The generators were wound for low voltage, so that the lamps could be operated directly from them. Power stations were erected at the centers of distribution. As the load increased, the size of the conductors necessary to give any kind of regulation became very large, and the cost of copper was enormous. Edison was the first to devise a means of effecting an economy in the weight of copper necessary to transmit a given amount of power, and brought out the Edison three-wire system, by which it was only necessary to use about 3/8 of the copper employed with the old two-wire system. This system is still used in both direct and alternating current distributions for lighting. Edison made use of the fact that by doubling the voltage, only 1/4 the weight of the copper would be necessary, but he added a middle or neutral wire whose voltage was halfway between the outside wires, so that the voltage between the outside wires was 240 and between either outside and the neutral was 120. The lamps were connected between either outside wire and the neutral serving merely to carry the difference in the currents. If therefore the number of lamps on each side was the same, the neutral carried no current. If the lamps were properly distributed, it was possible to make the unbalancing current small, so that the neutral wire could be made smaller than the two outside wires. At the power station, the 120-volt machines were connected in series, and the neutral wire ran from the middle connection. This was, of course, a great step ahead, as it permitted the transmission of power to greater distances, but the main advantage was the improved regulation, i.e., the increased steadiness of the lights. Even this system, however, was only good for several miles, and therefore did not enable the power station to be removed to a location where fuel and water could be more economically obtained. The system is, however, good for congested districts where the lines are short. Upon the introduction of the electric railway, the necessity for high voltage was forcibly impressed, and 500 to 600 volts soon became the standard and has remained so until the present time. With this increased voltage, it became possible to remove the power stations to a point of convenient water and fuel supply. Cars could then be operated fairly well over a radius of 5 or 6 miles without expending too much on the feeder cables. For several years previous to 1890, Nikola Tesla had experimented with alternating currents with a view to the production of an alternating current motor, and was at last successful. About the same time, transformers for raising and lowering the voltage were brought out, and the rotary converter for changing alternating into direct current was exhibited in 1893. This completed the steps in the development of the present alternating current system. The high-voltage alternating current generator in the railway powerhouse gradually displaced the direct current, and the power became concentrated in one large station, resulting in a more economical production of power. During this evolution, the railway lines remained in operation on direct current at 600 volts. This radically increased the radius of transmission. Substations were erected in various parts of the city, and in these were installed the rotary converters. The power from the central station was all sent out at high voltage as alternating current to transformers, from the low voltage sides of which it entered the rotary converter, which changed it into 600-volt direct current. Each substation, therefore, acted as a supply station, but without the large cost of a generating station. The lines supplied by each substation were comparatively short, and the voltage of the current remained much more nearly constant than before. One of the largest and most modern examples of this system of distribution is that of the Interborough Rapid Transit Company of New York City. Each of the generating units consists of a compound engine and a generator of 3.750 kilowatt capacity, delivering 25-cycle alternating current at 11,000 volts. The power is sent out at this voltage directly without the use of raising transformers and delivered to substations along the subway lines. At these stations, it is then reduced by means of lowering transformers to such a voltage that when applied to the rotary converter, direct current will be delivered at 600 volts, which current operates the railway motors. This system may be said to have become standard for large cities. Cables for underground use can now be made which are entirely reliable and satisfactory on 11,000 volts. This voltage is, however, as high as engineers will willingly guarantee and dispenses with the use of the large raising transformers necessary with the lower voltage generators. The first transmission of power to a distance in the United States was made in the year 1890, 1 year before the Frankfurt-Laufen experiment. This station was at the falls of the Willamette River in Oregon, 13 miles from Portland, where water power estimated at 225,000 horsepower is obtainable. In 1893, it had been in successful operation for 3 years with satisfactory results, both as to the working of the apparatus and the cost of maintenance, the operation of the dynamos being described as admirable and the transformers not having cost a cent for repairs. The plant, however, to which much of the present knowledge of conditions affecting high-voltage operation is due, is that of the Telluride Power Company in Colorado. This plant operates under particularly severe conditions, and in the overcoming of the obstacles encountered, much valuable information was gathered. Here, for the first time, men were systematically trained for operating the plant, each man receiving a general education in all the branches of engineering connected with it. Much of its success was, therefore, due to the knowledge and skill of its operating force. Here that natural enemy of long-distance transmission, lightning, was met and conquered. Near Telluride, Colorado, says Atkinson, is a water power station from which power is electrically transmitted to the Gold King Mill, nearly 3 miles distant, where it is employed for operating crushers and stamps. It was equipped, when first constructed, with a Westinghouse alternating current dynamo of 100 horsepower, operated by a Pelton turbine wheel driven by water received through a steel pipe 2 feet in diameter under a head of 320 feet. The general construction of this dynamo is the same as that of the dynamos employed at the Willamette Falls station, but its field winding is composite, part of the magnets being excited by the armature current of a separate direct current machine, and the others by a current from its own armature, which is made by an apparatus equivalent to a 2-segment commutator, the adjustment being such that the EMF of the current delivered through the mains rises as the current strength increases, compensating for the fall of potential in the line and keeping the EMF at the motor constant at 3,000 volts. The speed is 83 revolutions per minute, producing 10,000 alternations of current. The main current flows directly to the motor at the mill without transformation, the only transformers employed being the small ones connected with the indicators on the shunt circuits. The motor is the same in size, horsepower, and general construction as the dynamo, and runs in synchronization with it, but is excited by a current from its own armature, obtained from a special winding parallel with the main armature coils, and connected with the field coils by a circuit in which the current is made direct by a commutator. A small Tesla motor of special construction is employed as a starter for the large motor, and is connected with the mains by a parallel circuit, as shown. The armatures of both motors are belted to a countershaft on which the ratio of size between the pulleys is such as to give the armature of the large motor a little higher speed than that of the small one. When the circuit of the small motor is closed, its armature quickly attains its normal speed, putting the armature of the large one in rotation at a speed somewhat higher than that of the dynamo, and causing it to generate a self-exciting current at the normal EMF of the circuit. The small motor is then switched off, and the speed of the large one gradually decreases till it is approximately equal to that of the dynamo, the relative speed of each machine being indicated by the degree of illumination in incandescent lamps connected in series with the secondary coils of the 2 transformers, whose primary coils are connected, respectively, with the circuit of each machine, as shown. The illumination decreasing from decrease of current as the speeds of the 2 machines approach equality. When the proper relative speed, as thus indicated, is attained, the main circuit of the large motor is closed by its switch, and it is connected with the mill machinery by its friction clutch, the small motor having been disconnected by its clutch and brought to rest. The whole operation of starting is accomplished in about 2 minutes by 1 man. If the speed of the motor, on starting, should happen to be a little lower than that of the dynamo, it may rise to the proper speed, but if much lower, it will continue to decrease, in which case the switch of the large motor is opened and that of the small one closed, and the speed thus restored. The field current of the motor, as indicated by the ammeter, is regulated on starting by a rheostat and requires no further adjustment for the varying loads. The line runs across a rough country, ascending a mountain at the power station to a height of 2,500 feet, at an angle in some places of 45 degrees, and parts of it are practically inaccessible in winter, the snow being sometimes on a level with the tops of the poles. Special protection is required against lightning, to which this region is peculiarly liable, 40 discharges through the lightning arresters having, on one occasion, occurred in 40 minutes. The successful operation of the plant under these unfavorable line conditions, and with a comparatively new type of electrical apparatus since its completion in June 1891, has inspired such confidence that extensive additions have been made both for power and lighting, which indicates that the former purpose, as well as the latter the employment of the alternating current with long-distance transmission, has passed from the experimental to the practical stage. Since the above writing, many trials of high voltage have been made at this plant, until it is now operating at 40,000 volts. The Niagara Falls power transmission was one of the earliest, and is still the largest. The first station was built upon the American side and contains 10 5,000 horsepower, two-phase, 25-cycle, 2,200-volt alternating current generators. Each of these generators is mounted at the top of a long vertical shaft, at the lower end of which is the turbine. Since the weight of the generator and turbine is very great, too great to be supported by a bearing, the turbine is so constructed that the action of the water tends to balance this weight. The armatures of the generators are stationary, and the field magnets revolve outside the armature, being shaped like an umbrella. The best engineering skill in the world was employed in designing the plant, and its success is largely due to that fact. Turbine wheels and generators of that size were practically unknown, and the starting of the plant marked the beginning of a new era in the development of large water powers. Since the construction of the first plant, another similar one has been built, containing 11 units of the same capacity, making total output of the two plants 105,000 horsepower. Two other plants have also been constructed on the Canadian side of the river, which deliver part of their power to towns in the United States. Most of the power from the two American plants is consumed by local manufactories, which have sprung up there. 30,000 horsepower is sent to the city of Buffalo, about 25 miles away. Since power can be transmitted with 25% less copper with three-phase than with two-phase current, the two-phase current, generated at 2,200 volts, is changed by transformers to three-phase, and the voltage at the same time is raised to 22,000. The distance to which Niagara Falls is transmitting its power is increasing daily, the greatest distance being to Syracuse, 160 miles away, where power is delivered at 60,000 volts. A typical water power station, with a transmission line which is said to be, at present, the longest in the world, is that of the Bay Counties Power Company of California. This transmission system, says R. W. Hutchinson in his long-distance power transmission, is the longest in existence and was first put in operation on April 27, 1901. The company supplies power from 3 plants operated in parallel. Power is transmitted at 40,000 volts to Oakland, a distance of 142 miles from the main generating station, and power is supplied to the Standard Electric Company for transmission to various points along San Francisco Bay, the farthest of which is Stockton, 218 miles distant from the main power plant. Although long-distance power transmission by continuous currents is practically unknown in this country, there are many examples of this type in Europe, which have operated in competition with alternating current, and which are still being installed. Most of these plants are located in Switzerland and France, and are in satisfactory operation at present. Much of the development in continuous current working has been due to Monsieur Thury, a French engineer and the originator of the system which bears his name. In this system, a number of series-wound generators are connected in series so that their voltages add together. It is evident, therefore, that any voltage may be generated by connecting together a sufficient number of such machines, and 60,000 volts have in this manner been obtained. Direct current generators of this type can be built which will operate satisfactorily as high as 4,000 volts. In obtaining the 60,000 volts above mentioned, 16 of these generators are connected in series. Each machine is substantially insulated, both from the floor and from its driving turbine. The Thury system is known as a constant current system because the current is held constant no matter what the load may be, but the voltage is varied so that at light loads the voltage is low and reaches its maximum only at times of full load. The line is very simply constructed, consisting of 2 wires, and in case of accident to one wire, the earth may be used as a return. The line, therefore, presents a much simpler construction than that for an alternating current system requiring 3 wires. At the receiving end, the electrical power is converted into mechanical power through a number of series motors connected in series across the line. A centrifugal governor attached to each motor holds its speed constant by varying its field strength. For this purpose, a portion of the current, which is always the same, is shunted from the field through a resistance. What are the advantages and disadvantages of this system? The chief advantage claimed for it by its advocates is the simplicity of its line construction. With direct current, the insulation of the line is only subjected to the effective voltage of the line, while in an alternating current transmission, the voltage which the insulators must stand is at least 1.4 times the effective line voltage. And, in addition, surges of waves of voltage are liable to occur which may double this value. It will therefore be apparent that the direct current line has a decided advantage. Another advantage claimed for it is its ability to operate during lightning discharges, since more effective arrangements may be made to prevent the lightning from entering the stations. Coming to the stations, however, the direct current system has serious drawbacks. It has not been found practicable as yet to build the generators larger than 400 kilowatts output. To equal one of the Niagara Falls power stations in output would, therefore, take 125 such generators. Advocates for the alternating current system have always considered these stations too complicated for satisfactory operation. It must be admitted, however, that M. Thury, through persistent work, has simplified the station to such an extent as fully to meet this objection. On the whole, alternating current transmission seems to be more satisfactory than the direct current, and this advantage will increase as alternating current motors reach the perfection attained by direct current machines and line insulation becomes so perfected as easily to withstand the voltages imposed upon it. Regarding recent developments in high-voltage transmission and its future limits, the Engineering Record, August 15, 1908, says, "It is just now worthy of special comment that the record for high voltage has again been raised, this time to the soaring figure of 110,000 volts. For once, the palm for sensational engineering has left the Pacific coast, to repose, for a while at least, in the custody of the Central States. This latest step forward must really be regarded as epoch-making, since it carries the art of power transmission from the region of the tried and standard into the unknown country beyond. And the best of it is that the new incursion has apparently been a victory. It is a new proof that all things come to him who dares. At last the next great step has been taken, thanks to the enterprise of the insulator maker, and especially to the construction of the suspension type of insulator, which makes relatively easy pressures before difficult. The pin insulator, when constructed of dimensions adequate for very high voltage, becomes unwieldy and mechanically troublesome. Not so the suspension insulator, which actually leads to improvements in line construction. It will probably be found, too, as is often the case, that the precautions now considered necessary in going to very high voltages will prove to be more than adequate in the light of practical experience. It is a fact that in the continental practice surprisingly small and simple insulators have been found entirely successful for pressures considerably higher than would be attempted with the same material here. American engineers attach great importance to preserving a high line insulation, as they should, but they went through a period in which the size of insulator was all out of proportion to their quality and design. Now, practice is settling into sounder lines and will go on to better and better results. The fact is that at every stage of progress towards a high voltage, advance has been proved to be easier than seemed at first possible. Difficulties that seemed insuperable have been, time and again, overcome with comparative ease, so that now one is not beside the mark in counting upon a very great advance in the near future. Of course, the plants in which 100,000 volts or more is a figure commercially necessary are relatively few. As time goes on, however, and the more remote powers are utilized, High voltage will become more and more necessary and will be more generally employed. As to the limits which may be reached, one would be unwise to prophesy. At 100,000 or thereabout, a condition is reached where, save for large powers and long wires, further increase would lead to wires too small to be desirable mechanically. In addition, it is undesirable for electrical reasons to use anything much below a quarter inch in diameter at very high pressure, so that there is a natural limitation to the number of very high voltage plants. Yet, for the really big work of the future, success depends on just such bold achievements as the one here considered. The next step will probably be in the direction of a very long line at extreme voltage. Here, again, is a debatable ground, owing to line difficulties. No one has yet operated a line of such length as to be a material fraction of the natural wavelength corresponding to the frequency. There is a possibility of a new class of troubles arising under such circumstances, and new devices may be required to meet it. It is on such very long lines that the use of high-tension continuous current has found some advocates. Severe requirements as to the use of cables is a possible source of future trouble, but here also the manufacturer may be counted on to push ahead. 20,000-volt cable is in use in England to the extent of several hundred miles, and 40,000-volt cable has been successfully worked so that, if the time should demand underground lines at 100,000 volts or more, it is safe to say that they would be forthcoming. End of section 22. Section 23 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 6, The History of Electric Lighting, Part 1. The history of electric lighting begins soon after the discovery of electric currents. In 1800, Sir Humphrey Davy, while experimenting with the effects of currents, obtained bright sparks between two charcoal points upon breaking the contact between them. The number of cells with which he worked was, however, insufficient to produce a continuous light. After a few years, he increased the number of cells in his battery until it was composed of 2,000 elements. With this powerful source of current, he was able to obtain a continuous discharge between the carbon points, which sustained itself across a gap of 7 inches and emitted a dazzling light. This light was exhibited in 1813 at the Royal Institution. Davy found that the conducting power of the charcoal points was improved by extinguishing the charcoal under mercury. The consumption of these points was very rapid. The name voltaic arc came from this experiment of Davy's, from the fact that the stream of vapor formed itself into a bow, the charcoal points being horizontal. Owing to the high cost of producing the electric current, no one seems to have cared either to develop a lamp or to ascertain the properties of the arc itself until 1844, when Foucault constructed a lamp using carbons from the retorts of gasworks, which were much harder and more compact than Davy's charcoal points and less easily consumed. Thomas Wright of London devised the first apparatus, 1845, in which the adjustment of the carbons is brought about automatically. W.C. Straight used the electric current for the regulation of the carbons in 1848. In 1858, Foucault devised a lamp in which the carbons were made to approach automatically by means of a clockwork feed, the clockwork being controlled by an electromagnet. As the current diminished in strength due to the increase in the length of the arc as the carbons burned away, a magnet in series with the arc weakened and released the escapement of the clockwork, thus moving the carbons together. In this lamp, both carbons moved, and were so regulated in their motions as to maintain the arc in a fixed position. In later lamps, used for general illumination, this was not considered necessary, and the regulating mechanism was considerably simplified. The lamps were known as focusing or self-centering lamps, and are still necessary in some cases, such as stereopticon work. Before proceeding with the history, some of the properties of the arc may be examined. If it is attempted to produce an arc by means of a few cells of battery, the attempt will be unsuccessful. It is necessary that a difference of potential of about 40 volts should exist between the carbons before any stream of vapor will be formed. The longer the arc produced, the higher is the voltage necessary to maintain it. In the ordinary carbon lamp, practically no light comes from the arc itself. It is all emitted from the white-hot carbon points. If the source of current is direct or continuous, most of the light is radiated from the positive carbon, or that by which the current enters, and this carbon is consumed about twice as rapidly as the other. From this fact it will be seen that in such lamps as Foucault's, it was necessary to arrange the mechanism so that the positive carbon should move at about twice the rate of the negative. Another peculiarity is the manner in which the carbon points burn away. When the combustion takes place in the air, the positive carbon has a depression or crater formed in it, and upon the negative is produced a nib. This seems to be due entirely to the fact that combustion takes place in air, as the phenomenon disappears when the arc is enclosed and both carbons become blunt. This seemingly slight difference was, however, a factor of considerable consequence, as the greater part of the light is emitted from the intensely hot crater of the positive carbon, so that in the open arc much of the light is cut off from the horizontal direction by the rim of the crater, which is removed by enclosing the arc. The temperature of the arc is the greatest of all earthly temperatures, nearly all substances volatilizing almost instantly. Arc lamp development was stimulated by the construction of the magneto-electric machine, which greatly decreased the cost of power. The introduction of the dynamo, however, completely solved the problem of power, and the field was immediately opened for the electric light. One of the first successful lights was the electric candle of Paul Jablokov, invented in 1876. This is probably the simplest of all electric lamps. As shown in Figure 22, it consists of two carbon rods placed parallel and separated from each other by plaster of Paris, the rods having brass tubes at their lower ends which make contact with springs set in the holding device. To start the candle, a thin plate of graphite was laid across the tip, this being heated by the passage of the current sufficiently to start the arc. Difficulty was, of course, encountered in operating these lamps on direct current on account of the unequal rates of burning of the positive and negative carbons. It was attempted to overcome this by making the positives twice as thick as the negative carbon, but the ratio not being exact and liable to variation caused the failure of this method. They were therefore operated on alternating current, and over 4,000 were used in Paris alone. The lamps, however, were not satisfactory, and inventors gradually reverted to the lamp with the adjustable mechanism. As soon as arc lamps had to be operated over considerable territory, it was seen that the mode of connection, known as a series, wherein a single wire is used to connect the lamps together, was preferable to the parallel system, which required two wires, both in economy of wire and in saving of power. This required a special arrangement of the lamp mechanism. On the series system, the same current passes through each lamp, and since it requires about 50 volts to operate a lamp, the generator must develop as many times 50 volts as there are lamps. This necessitated the construction of a generator which should develop a high voltage, as there were often as many as 125 lamps on one line, requiring 125 times 50, or 6,250 volts. Such a suitable generator was devised by Mr. Charles Brush, and is known as the Brush arc lighting dynamo. Returning to the mechanism of the lamps suitable for such a current, one of the first of these was constructed by Hefner Alternacht, and is known as the Siemens differential lamp. This type of regulator is still in use, although of course modified and improved. Figure 24 illustrates the method of regulating. The lower solenoid, R, is known as the series coil, and carries the same current that passes through the arc. The upper solenoid, T, has many turns of fine wire and is connected across the arc. The two coils act upon the same core in opposite directions, hence the name differential. If the carbons approach too closely, the current in the series coil increases and pulls them apart, but as the length of the arc is increased, thereby the voltage across it grows greater and the shunt coil T receives more current. This prevents the series coil from producing too great a motion, and the carbons are held by the balancing action of the two coils. The upper carbon alone is fed down by the action of gravity, the lower carbon being fixed. This style of lamp was also developed by Brush in America, and many thousands have been used. The combination of the Brush high-voltage generator and the differential series lamp was quite satisfactory as a means of lighting, and many of these arrangements are in use at the present time, although they are fast being replaced by more modern systems. With the open arc lamp of the brush type, the replacement of the carbons was required daily and became quite an item in the total expense of operation. About 15 years ago, arcs enclosed by thin glass were introduced, which required trimming only once in 10 or 15 days. At first it was thought that the enclosing glass would cut off so much of the light as to seriously impair the efficiency of the lamp. The fact previously mentioned concerning the flattening of the carbon tips and a consequent better distribution of the light here came to the aid of the enclosed lamp, so that although there was some loss of light due to the glass, the improved distribution overbalanced that effect. A grave fault, however, was the disposition of the siliceous impurities of the carbons on the enclosing glass, with a consequent diminution in light. Efforts were accordingly directed towards the improvement of the carbons, and although it had not been found possible to produce carbons free from such material, that fault is not at the present time serious. Although the series system in operation is the only practicable one over long distances, it is often required to operate arc and incandescent lamps on the same circuit as in buildings, etc. For such work, the differential mechanism of the series systems is not suitable. In that system, the lamps act to steady one another, for with so many in the circuit, the fluctuations of one lamp do not appreciably affect the current in the circuit. The operation of a single lamp requires, therefore, something to replace the steadying action of the other arcs, and this is accomplished by means of a dead resistance. Some energy is, of course, wasted in this resistance, about 25%, but the operation is very satisfactory. An ordinary carbon arc lamp, although one of our most efficient sources of light, is still far from the ideal. Of the total energy radiated from it, only about 10% has the proper frequency of vibration to affect the eye as light. The ideal light would emit rays, all of which would affect the eye. One means of effecting this increase is to raise the temperature of the heated body. Another, to employ a different material, since all materials do not emit equal light at the same temperature. Attempts to utilize the latter principle resulted in the production of luminous and flaming arcs. Some of the most prominent workers on the subject are Bremer, Auer, Nernst, Blondel, Whitney, and Steinmetz. The luminous arc is composed of two electrodes, which supply a stream of light-giving vapor. One of the most prominent examples of this type is that developed by Mr. Steinmetz and known as the magnetic arc. The positive electrode is a rod of copper, the negative a rod of magnetite or iron ore. The light given off is an intense greenish white, the efficiency being several times that of the ordinary arc. They have recently been established on a commercially operative basis, although still unsatisfactory in some respects. They can operate only on direct current, which usually involves the rectification of the alternating current, now almost universally generated. The flaming arc is almost invariably produced by utilizing the intense heat of the carbon arc to render incandescent various refractory materials. For this purpose, either one or both of the carbons are impregnated with metallic salts having great light-giving power, as calcium, titanium, strontium, etc. The most efficient of these are the salts of calcium, which emit dazzling yellow rays. For some purposes, as interior lighting, these rays are objectionable on account of the distortion of color which they produce, and the salts of titanium are preferred, as these emit a beautiful white light, although of less intensity. The lamps may be operated on either direct or alternating current. The objectionable features of these lamps are the increased cost of the carbons and their short life. For that reason, they have not yet come into general use for street lighting. In respect of life, the magnetic arc has the advantage, its life being about the same as the enclosed carbon arc, 150 hours. Developments in arc lighting have followed one another with such rapidity during the last 7 or 8 years and are still progressing so swiftly that one hardly knows where they will stop. The fine organizations of engineering and scientific skill under the control of large electrical enterprises have made possible these rapid developments of the last few years. Admirable as is the system of electric arc lighting for use in streets and open spaces, and in workshops or large halls, says Henry Morton in his Electricity in Lighting, It is entirely unfit to take the place of numerous lights of moderate intensity employed for general domestic illumination. For this purpose it was at a very early period perceived that the incandescence, or heating to luminosity, of a continuous conductor by an electric current was the most promising method. It was also at a very early period perceived that the conductor to be used for this purpose must be one which would admit of being raised to a very high temperature without being melted or otherwise destroyed. The first material which was thought of in this connection was platinum, or one of its allied metals, such as iridium, which have the highest melting points among such bodies, and are, besides, entirely unacted upon by the air at all temperatures. In 1848, W. E. Straight took out a patent for making electric lamps of iridium or iridium alloys, shaped into an arc or horseshoe form. One of the most serious difficulties, however, even with these materials, was that to secure from them an efficient light it was necessary to bring them so near to their fusing points that a very minute increase in the current would carry the temperature beyond this and destroy the lamp by fusing the conductor. An escape from the difficulty was offered by the use of hard carbon, such as that employed for the electrodes of arc lamps. But here the compensating drawback was encountered in that this substance, when highly heated, was attacked by the oxygen of the air, or, in other words, burned. To meet this, plans were devised for the replacement of the consumed carbon in a non-active gas, or in a vacuum. Thus, in 1845, a patent was taken out in England by Augustus King, acting as an agent for an American inventor named J. W. Starr, for an incandescent lamp, the important parts of which are represented in Figure 23. Here a platinum wire is sealed through the top of a small glass chamber, constituting the upper end of a barometer tube. This platinum wire carries at its power end a clamp, which grasps a thin plate or rod of carbon, and also a non-conducting vertical rod or support, which helps to sustain another clamp, which grasps the lower end of the carbon strip and connects it by a wire with the mercury in the barometer tube below. By passing a current through the platinum wire and thence through the upper clamp, carbon strip, lower clamp, wire, and mercury, the carbon strip could be made incandescent and was to a certain extent protected by the surrounding vacuum. Though this lamp produced a brilliant light, it proved in various respects unsatisfactory and was abandoned after numerous trials. Other inventors, as for example Kuhn of St. Petersburg, continued to work with rods or pencils of hard carbon and achieved a limited success, but the irregularity and brittleness of the material seemed to have been an insuperable objection and drawback, and the problem of commercial electric lighting by incandescent conductors yet remained without solution. This was the state of affairs even up to the fall of 1878, when, as is claimed, William E. Sawyer, in combination with Alban Mann, after many preliminary experiments, produced their first successful incandescent lamp with an arc-shaped conductor made of carbonized paper. In their application for a patent, filed January 8, 1889, these inventors used the following remarkable language in their fourth claim: an incandescing arc of carbonized fibrous or textile material. This indicates that they realized the importance of what seem to be the common features of the present incandescent lamps, namely, the arc or arch or bow or loop form and the carbonized fibrous or textile material. They also specially refer to carbon incandescent conductors made from paper. After a long and hotly contested interference, the United States Patent Office has granted them a patent in which these points are broadly stated. The lamp brought out by Messrs. Sawyer and Mann soon after their application for a patent, and described and shown in that application, was a rather large and complicated structure, and had no improvement and simplification of this structure been made, the present immense development in electric lighting would no doubt have been unattained. It is to T. A. Edison, without doubt, that we owe many of the simplifications and modifications which, by cheapening the lamp and diminishing its weight, have extended its range of use and its usefulness to a remarkable degree. On his return in the fall of 1878 from the far west, where he had gone in company with Dr. and Mrs. Henry Draper, Dr. George P. Barker, and the present writer to observe the total solar eclipse of that year, Mr. Edison visited the shops and laboratory of William Wallace at Ansonia, Connecticut, where many experiments with electric arc lights and dynamo machines were in progress, and while studying these, was impressed with the desirability of producing an incandescent electric lamp. Like so many before him, he first turned to platinum and platinum alloys and devised a form of lamp admirable for its simplicity, but, unfortunately, open to fatal objection. This first lamp of Edison's is shown in Figure 25, in which AB is the incandescent platinum wire. The announcement of a new system of electric lighting made by Mr. Edison and his friends on the foundation of this device attracted universal attention and even caused a serious fall in the value of gas stocks in the country and abroad. It is, indeed, amusing now to look back upon the extravagant assertions and predictions made at that time and widely circulated when we realize how more than frail was their foundation. In fact, Mr. Edison very soon found out that this simple device was entirely insufficient for the purpose proposed, because the heated platinum wire gradually stretched by its own weight and thus was constantly getting out of adjustment, and finally would become attenuated and break. It also happened that, though the secret of this great invention was carefully guarded, some inkling of it escaped, and this enabled those who were familiar with such subjects to perceive the close similarity between this Edison lamp and a similar device constructed and used by Dr. J.W. Draper prior to 1847 and described and figured in articles published by him during that year in the American Journal of Science and Arts, the London, Edinburgh, and Dublin Philosophical Magazine, and Harper's New Monthly Magazine. This apparatus was used by Dr. Draper as the source of light or lamp with which he determined the relations between temperature and luminosity. At the conclusion of this article, Dr. Draper says, "An ingenious artist would have very little difficulty, by taking advantage of the movements of the lever, in making self-acting apparatus in which the platinum should be maintained at a uniform temperature, notwithstanding any change taking place in the voltaic current." It also appeared that precisely the same idea had occurred to another inventor, Hiram S. Maxim, who has recently developed such marvelous improvements in magazine or repeating guns, and who, on December 22, 1879, filed an application for a patent which, after an interference litigation with Edison, was finally issued to Maxim on September 20, 1881, for the form of electric lamp shown in Figure 26. It has also been shown that in 1858, M.G. Farmer, one of the veteran electricians of America, to whose work in connection with the dynamo-electric machine allusion has been made before, lighted a room in his house at Salem, Massachusetts, for several months with platinum lamps of similar structure, controlled by automatic regulators. During 1878 and 1879, however, Mr. Edison was most diligently at work, and perceiving the imperfections of his first ideas, sought in every way to overcome them. It thus came to pass that by December 21, 1879, at which date he made his first revelation to the public in the pages of the New York Herald, he had perfected a platinum lamp, which is shown in outline in Figure 27, as well as some other forms substantially like it. But these platinum conductor lamps were not the only outcome of Mr. Edison's work between the fall of 1878 and December 1879. As this Herald article related, Mr. Edison, like many before him, having experienced the insuperable difficulties present in metallic conductors, had turned his attention to carbon in various forms, and like Sawyer and Mann, had found fibrous textile materials, when carbonized, to be most convenient, and paper especially to be, in the first instance, the most available substance. Like Sawyer and Mann, he had also found the arc, or horseshoe form, to be the most desirable. Though working with the same materials and form, Edison produced a structure very different in appearance from that of Sawyer and Mann, as will be seen by a reference to Figure 28, which represents one of Edison's paper-carbon lamps, which was the first one whose electric properties were accurately measured, these measurements having been made at the Stevens Institute of Technology early in 1880 by the present writer, acting in his capacity as chairman of the Committee on Scientific Tests of the United States Lighthouse Board, that body desiring information as to this new light and deputing the work of investigation to this committee. In this lamp, the carbon conductor is supported on platinum wires and held in minute platinum clamps at the ends of these wires, which are sealed through the walls of the pear-shaped enclosing tube in a manner which has been familiar for 20 years in the construction of the beautiful toys known as Geissler tubes. The interior of this glass vessel has likewise been exhausted and hermeneutically sealed in the manner usual with many Geissler tubes and with the radiometers of Dr. William Crookes. Since its invention, the Edison lamp has maintained a practical monopoly, and it is only within the last few years that other competitors have loomed up which threaten its supremacy. They still have difficulties to surmount, however, which have already been overcome in the carbon filament lamp. End of section 23. Section 24 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 6, History of Electric Lighting, Part 2. Edison's first filaments were made of carbonized thread or paper. It is obvious that such filaments could not be made with any great uniformity. A great many experiments were made and are still being made to determine the best method of making them. They are all, however, made by what is called the squirting process, of which an outline follows. Pure cellulose, as cotton wool or blotting paper, is dissolved in a concentrated solution of zinc chloride until a jelly-like mass is obtained. Great care is required to obtain pure materials, and the various processes must be closely watched. This mass is filtered by forcing it through a suitable filter such as glass wool, fine wire gauze, or flannel. It is then heated under a vacuum to free the viscous material from air carried into it by the cotton wool or cellulose. It is then squirted under fairly high pressure through a fine orifice, which just dips below the surface of acidified alcohol contained in a tall glass jar. The alcohol hardens the cellulose, which forms a fine thread of a diameter depending on the size of the orifice. By revolving the jar, the thread is coiled in it. When hard, it is removed and washed and wound on drums to dry. When dry, it has the appearance of catgut. It is then given the desired shape by being wound on molds and baked. Bundles of filaments are then packed in carbon powder in plumbago crucibles, which are raised to as high a temperature as possible. The carbonized filaments are gauged for diameter and the legs cut to the required length, after which they are ready for mounting on the leading-in wires. There are two methods for doing this. In one, the ends are laid against the leading-in wires and a drop of paste composed of graphite mixed with a binding material is applied, the paste being afterwards dried in an oven. The other, by heating the joint red hot in an atmosphere of benzene, the benzene having decomposed and carbon deposited. The filament is then flashed in order to make it more uniform and increase its life. Flashing is accomplished by placing the filament under a bell jar filled with hydrocarbon vapor and raising it to incandescence by the passage of a current, whereupon the vapor is decomposed and a firm, compact coating of carbon is deposited upon it. The greatest deposit takes place where the filament is thinnest, as the current causes it to heat most in that part. Flashing therefore smooths out the irregularities of the filament. The filaments are next sealed into bulbs and the bulb exhausted. In the early days, Sprengel mercury pumps were used, but these were very slow, although very perfect. Nowadays, a little phosphorus dissolved in alcohol is introduced into the stem, which is then connected to a mechanical air pump having oil-sealed valves and exhausted as far as possible. The stem is then sealed for a short distance below the bulb and the phosphorus vaporized by a little heat into the bulb, where it combines with the remaining oxygen and completes the exhaustion. The lamp is then properly sealed off. The first patents covering the principles of the Nernst lamp were taken out by Professor W. Nernst in 1897 and 1898. In its first form, it was very crude, serving mainly to show the fact that the filaments could be produced, and that their efficiency was about twice that of the ordinary carbon filament. This was the first incandescent lamp to threaten the life of the Edison carbon filament lamp. Much was promised for it at first, and its development was vigorously taken up in this country, England and Germany. Although the lamps are still manufactured, very few are in use, and it is probable that the manufacture of them will soon cease entirely. The recent introduction of the tungsten lamp has made its existence unnecessary, as it is surpassed by the tungsten lamp in efficiency, life, and first cost. It contains, however, a very interesting principle, viz., the employment of an electrolytic conductor as the incandescent body. The conductor, or glower, as it is called, is practically non-conducting at ordinary temperatures and requires to be heated before it will allow the passage of current through it. This fact is probably the principal cause of its failure commercially, as the heating apparatus is quite complicated, of uncertain life, and the time consumed in lighting, sometimes half a minute, is in many cases objectionable. This is the only electric lamp that can be started with a match and blown out. The glower of the American form of Nernst lamp is said to consist of the oxides of several rare metals, such as yttrium, ytterbium, thorium, etc., although the true composition is known only to a few. The glowers are in the form of a short, thick filament, cemented to flexible platinum terminals by which it is suspended below and close to heating coils consisting of porcelain tubes in which are embedded resistance wires. These resistance coils are, of course, necessary to bring the glower up to the temperature at which it begins to conduct. The heating resistance is connected in shunt with the glower, which has in its immediate circuit an electromagnetic switch for opening the heater circuit. When the glower becomes sufficiently heated to conduct, the current in this portion of the circuit operates the electromagnetic switch and automatically cuts out the heating coils. As the glower conducts electrolytically rather than as a solid, up to the present it has given a much shorter life when used on direct or low-frequency alternating current circuits than with higher frequencies. Although up to the present time these lamps cannot be called a commercial success, recent developments and improvements in constructional details have made the efficiency of the lamp equal to that of tungsten. If a method of producing a lamp free from the complicating starting apparatus which now prevails is discovered, these lamps may be heard from again. These lamps have followed one another in such rapid succession that some of them, although full of promise, have never been long in the commercial field, having been succeeded by others still better. Incandescent electric lamps with metallic filaments are older than carbon filament lamps. As long ago as 1840, lamps were constructed with filaments of platinum, and for 30 years after that date, various attempts were made to construct a practical lamp using either platinum or iridium wires for the filaments, the only two metals at all suitable which were obtainable at the time. None of these attempts met with any commercial success, and the use of metals was finally abandoned in favor of carbon by the experimenters who developed the carbon filament lamp in 1878 to 1880. The success attained with carbon caused all consideration of metallic filaments to be put on one side for nearly 20 years. The introduction of the Nernst lamp appears to have then stimulated research afresh, and many investigators turned their attention to the metals, to find the field greatly widened by the chemical progress which had been made in the meantime. Instead of only two possible metals to work with, there were now numbers known with sufficiently high melting points to suggest great possibilities. After much painstaking effort and laborious work carried out by inventors who deserve the highest possible praise for both their ingenuity and their perseverance, 3 commercial metallic filament lamps have been evolved, which have entirely altered the outlook for the future of the electric lighting industry. It is possible, suggests Maurice Solomon in his Electric Lamps, that these may prove to be only the forerunners of further improvements. Rumors of fresh developments are of almost weekly occurrence, and it is difficult to say at the moment what is likely to be the course of events during the next few years. Up to the present, none of the rumored improvements have given any evidence of being advanced beyond the laboratory stage, and many do not appear even to have reached that stage, though some have been proved commercial, namely the osmium, tantalum, and tungsten, wolfram or Orsum lamps. The osmium lamp is the invention of Dr. Auer von Welsbach, and the earliest patents relating to it were taken out in 1898. The earlier reports in reference to the osmium lamps appeared in the technical press in 1901, but the lamp does not appear to have been manufactured commercially until 1903, and it was not until 1905 that it was introduced into this country by the General Electric Company. The method of manufacture may be gleaned from the patents and from a paper read by Dr. Fritz Blau before the Elektrotechnischer Verein in 1905. The process first tried was that of flashing platinum wire in an atmosphere of osmium tetroxide, which is volatile. By subsequently incandescing the alloy in vacuo, the platinum can be evaporated off, but it was not found possible to produce sufficiently thin filaments in this way. Finally, the method adopted was that of pressing finely divided osmium mixed with an organic binding agent through small diamond or sapphire dies. The thread thus formed is carbonized, and the carbon is then driven off by encasing the filament in an atmosphere of steam and hydrogen. The filaments have to be raised to a very high temperature in order to sinter together the osmium particles into a practically homogeneous filament. Sintering may be described as a sort of modified welding process. The metal does not fuse, but the particles raised almost to their melting point bake together and bind very firmly. As a matter of fact, exactly the same phenomenon occurs with carbon filaments, which after the first stages of baking are highly porous, but become dense and homogeneous on further raising their temperature. The osmium filaments are mounted in bulbs in the same way as carbon filaments, the mount being made by fixing together by means of an arc at the end of the osmium filament and the leading in wire. The osmium lamp has been described on account of its interesting position as the first of the new metallic filament lamps. The lamp must be regarded at present as already obsolete, having given place to the tungsten lamp, the filament of which is similar in character to the osmium filament, but in many respects superior. The earliest patents in relation to the tantalum lamp were taken down by Messrs. Siemens and Halske in 1901 and 1902, but the lamp was not introduced commercially until 1905. During 1906 and 1907, the lamp has steadily grown in popularity, and the number now in use is very large. The tantalum lamp can certainly claim to be the first metallic filament lamp which proved to the full its suitability by the development of its formidable rival, the tungsten lamp, and it will continue to be remembered as the first lamp to afford solid ground for the hope of a marked advance in electric incandescent lighting. The filament of the tantalum lamp is made from pure drawn tantalum wire, and one of the chief difficulties in its manufacture is the preparation of the pure tantalum in a form suitable for drawing. Tantalum metal is obtained in a powdery form by reducing potassium tantalofluoride. The powder is then fused electrically in vacuo, the process serving not only to produce the metal in a coherent form, but also to drive off the occluded gases. The fused ingot is drawn into wire, the precise method by which this is done not being published, but the process must be one of considerable difficulty in view of the extreme hardness of the metal, which is, however, ductile, and the tantalum wires are quite flexible. The metal oxidizes readily, and when heated burns away completely to oxide. The filament must therefore be mounted in an exhausted bulb, and the difficulty of disposing of the necessary length in the bulb has been overcome in an ingenious manner, rendered possible by the flexibility of the wire, by winding it on a frame as shown in Figure 29. In this figure, for the sake of greater clearness, only the front half of the frame and filament is shown. This frame is mounted in a bulb in the usual manner. The other details of the lamp call for no special mention. Probably apart from the difficulty in making the original tantalum wire, the lamp is one of the easiest of the metallic filament lamps to manufacture, which leads to the hope that it may be greatly reduced in price when competition renders this necessary. The earliest patents relating to production of filaments of tungsten appear in 1904. The most important of these are taken out by Just and Hahnemann, Kutzel, and Welsbach. In 1905 and 1906, many other patentees covered processes for manufacturing these filaments, but it must be remembered that by this time, the possibilities of the metallic filament lamp were becoming well recognized, and many who patented methods and processes probably did so only in the hope that their ideas might someday prove fruitful. The credit for the development of a commercial lamp rests with the inventors already named, and lamps are now manufactured by all three of the processes which they devised. It is too early to say which of these is likely to survive. Possibly some modification, combining the advantages of all, will prove ultimately the most efficient and reliable manufacturing process. The tungsten lamp appears to have a brilliant future before it. While its present form lacks some of the advantages of the tantalum lamp, the fact that the consumption of power per candle is only about half that with tantalum will cover a great many defects. Unless a new metal filament is brought forward with an efficiency markedly superior, it is difficult to see what competitor now in the field can stand long against the tungsten filament. The commercial development of the tungsten lamp has been conducted with marvelous rapidity. Everywhere they are rapidly displacing carbon filament lamps. Their fragility, however, restricts their use to places where they are not subjected to mechanical vibration, although by ingenious methods of mounting this defect is fast being overcome. The idea of producing light from incandescent vapors has always been an attractive one. Theoretically, it is possible to obtain a far more efficient light from these vapors than from incandescent solids, because the emanations are more nearly of the same frequency than those from solids. Discharges in vacuum tubes have been tried for many years, and there was developed a form of tubes known as Geissler tubes, in which the most beautiful effects were produced by discharges through rarefied gases, but their brightness was never sufficient for practical lighting. About 10 years ago, Peter Cooper Hewitt, making use of the fact that a column of mercury vapor is a good conductor, succeeded in constructing a mercury vapor lamp of great power and efficiency. This lamp consists of a long glass tube having 2 electrodes, the negative of which is mercury. The arc is formed between these electrodes and completely fills the tube. This is therefore a true arc lamp. The lamp must be burned in an inclined position, the mercury being in constant circulation. It is vaporized at the lower end, condensed at the upper, and runs back to the lower again. One feature which for general lighting is objectionable is the color distortion produced by this light. Since there are no red rays in it, red bodies appear black, and all objects have a greenish-blue appearance. For purposes of photography, for drafting rooms, etc., it is, however, admirable, being rich in the upper rays of the spectrum. Following out the idea of producing light from discharges in a vacuum, Macfarlane Moore has succeeded in producing a lamp which is extremely ingenious. The chief advantage claimed is the improved distribution of the light being nowhere intense. The tubes may be made 100 or 2 feet long and may be fitted to suit the shape of the room. The discharge is effected by means of a high-voltage transformer. The tube gives off a pleasing light of a pink color. End of Chapter 6.
Section 25 of the Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 7, The Development of Electrochemistry. The striking effects brought about by electricity formed the subject of much study about the middle of the 18th century. At that time, friction electrical machines were in use, and in order to intensify the effects produced, very large machines were constructed. The most famous of these is still to be seen in the Taylor Museum in Haarlem. Peter Beccaria, some 130 years ago, by using such machines, found that metals could be revivified, that is, reduced, from their calces, oxides, when the electric spark was passed between 2 pieces. In this way, he obtained zinc and mercury. Some time later, Priestley investigated the action of the electric spark on air and observed that an acid was produced. He mistook this for carbonic acid until Cavendish recognized it as nitric acid. Van Marum studied the behavior of several other gases in this path of the electric spark, which led him to notice the formation of ozone, and made experiments also by passing the spark through liquids. Before him, Priestley had discovered that in oil and ether the electric spark produces gas, and proved that this gas contained hydrogen. The first actual electrolysis was made by Diemen and Paetz van Troostwijk in Haarlem in 1789, in which they successfully decomposed water into hydrogen and oxygen. In their experiments, the water was contained in a cylindrical tube closed at the top and having a metal wire sealed into its upper end. Another metal wire was introduced into the lower end of the tube, which dipped into a basin of water. When the spark struck through the water, bubbles of gas were disengaged from the metal wires and, rising in the tube, gradually displaced the water. As soon as the column of water sank below the upper electrode, the gas, which was a mixture of hydrogen and oxygen, exploded. This experiment was later repeated by Ritter using silver wires and a solution of a silver salt, and he observed that the negative pole became coated with precipitated silver. On changing the poles, silver was dissolved from one and deposited on the other, now the negative pole. In Diemen's experiment, oxygen and hydrogen were simultaneously formed, both at the positive and at the negative poles, so that the process was not a true electrolytic one like that of Ritter's. The whole state of the science was changed in a great degree by the discoveries of Galvani, and particularly by those of Volta. In 1795, Volta arranged the metals in a series according to their behavior in galvanic experiments, and in 1798 Ritter showed that the same series is obtained when the properties of the metals to separate other metals from their salt solutions are compared. Quote, "After the introduction of Volta's pile in 1800, the physiological and optical phenomena were less studied," unquote, remarks Sven Arrhenius in his Textbook of Electrochemistry. Quote, "And more attention was paid to the chemical actions. As opposed to the electrical machines, these piles gave large quantities of electricity at a comparatively low potential. Nicholson and Carlisle in 1800 studied the evolution of oxygen and hydrogen in salt solutions at immersed gold electrodes which were connected with the poles of a voltaic pile, and observed that litmus in the neighborhood of the positive pole was turned red by the acid produced there. Some years later, Davy made his brilliant electrochemical discoveries. He succeeded in decomposing the oxides of the alkali and alkaline earth metals, which had previously been regarded as elementary substances, and in preparing the pure metals. Further progress in obtaining the more difficultly reducible metals in this way was later made by Bunsen and his pupils." Unquote. At the time of Davy's discovery of the alkali metals, Berzelius was just beginning his scientific investigations. In one of the first of these, carried out jointly with Hisinger, he studied the action of the electric current upon solutions of various inorganic substances, resulting chiefly in the establishment of the first electrochemical theory. This theory dominated the science of chemistry for many decades. According to it, each chemical atom, when in contact with another, possesses, like a magnet, an electropositive and an electronegative pole. Moreover, one of these poles is usually much stronger than the other. Consequently, an atom behaves as if it possessed but one pole, either electropositive or electronegative, according as the positive or negative pole, respectively, predominates in strength. The magnitude and sign of this resultant polarity upon the atoms of a given element determines its chemical behavior. If, for instance, the atoms of an element are electropositive, it will react with elements whose atoms are electronegative, and conversely. During this reaction, the two kinds of electricity neutralize each other more or less completely according to the degree of inequality existing between the positive and negative charges upon the reacting atoms. If complete neutralization does not take place, the resulting compound itself is electropositive or electronegative, according as the electropositive are greater or less than the electronegative charges upon the component atoms. Compounds which thus possess a resultant polarity may then enter into further combinations with each other in such a way as to form a complex compound which is more nearly or quite neutral. Thus the theory explains not only the formation of simple compounds from their elements, but also the formation of complex compounds such as double salts from their component simple compounds. According to this theory, chemical and electrical processes are closely related, and all compounds have a dualistic nature, being formed of an electropositive and an electronegative component. This theory is therefore known as the electrochemical or dualistic theory. It was applied throughout the domain of inorganic chemistry, which at that time was practically the entire science of chemistry, and although it contained many arbitrary assumptions, it performed a great service to science because of its systematizing influence. For several decades after the establishment of the dualistic theory, no considerable advance was made in electrochemistry. This lack of progress was soon counterbalanced by the important discoveries which were made by Faraday about the year 1835. He was the first to show that whether electricity is produced by friction or by means of a voltaic pile, it is capable of producing the same effects. This fact convinced him that there exists but one kind of positive and one of negative electricity. He next attempted to discover a relation between the quantity of electricity flowing through a circuit and the magnitude of the chemical and magnetic effects which it could produce. His results may be expressed as follows. The magnitude of the chemical and magnetic effects produced in a circuit by an electric current is proportional to the quantity of electricity which passes through the current. A further discovery was made by Faraday by comparing the quantities of different substances in solution which are decomposed by the same quantity of electricity. This comparison may be made in a very simple manner by connecting into one circuit a series of solutions of different substances so that the same quantity of electricity passes through each solution. The chemical decomposition produced by the electric current in each solution may then be determined by analysis. The results obtained may be summarized as follows. The quantities of the different substances which separate at the electrodes throughout the circuit are directly proportional to their equivalent weights, and are independent of the concentration and the temperature of the solutions, the size of the electrodes, and all other circumstances. Those who first recognized the decomposition of water by the electric current sought an explanation for the simultaneous appearance of hydrogen at one electrode and of oxygen at the other. It was not until 1805, however, that a comprehensive theory for this phenomenon was put forward. During that year, such a theory was published by Grotius. According to this theory, the electric current charges one electrode positively and the other negatively, and these charged electrodes then exert an electrical influence upon the water molecules. Under this influence, the water molecules acquire a polarity, the hydrogen atom becoming charged with positive and the oxygen atom with negative electricity. The positive electrode then attracts the negatively charged oxygen atom, and the negative electrode the positively charged hydrogen atom, causing the water molecules to arrange themselves in a row or chain. As science gradually developed, the imperfections of the theory advanced by Grotius became more and more apparent. According to this theory, the splitting of the molecule, which is necessary for the conduction of electricity, cannot take place until the electromotive force is sufficiently great to overcome the affinity or cohesion between the two components of a given compound. As a matter of fact, however, it was found that, under suitable conditions of experiment, it is possible to cause an electric current to pass through a solution even when the electromotive force of the current is extremely small. Clausius was the first to direct attention to the disagreement of the Grotius theory or conception of electrolysis with facts. Basing his conclusions upon the experimental results already obtained, he declared, quote, "Every assumption to be inadmissible which requires the natural condition of a solution of an electrolyte to be one of equilibrium, in which every positive ion is firmly combined with its negative ion, and which at the same time requires the action of a definite force in order to change this condition of equilibrium into another, differing from it only in that some of the positive ions have combined with other negative ions than those with which they were formerly combined. Every such assumption is in contradiction to Ohm's law." Unquote. At about the same time that Clausius advanced this theory, Hittorf began work upon the migration of the ions, and a little later Kohlrausch commenced experiments upon the electrical conduction of solution. The work of these investigators greatly increased the knowledge of the process of electrolysis. Making use of their work, Arrhenius in 1887 replaced the theory of vibrating ions of Clausius by the theory of free ions. According to the material conception of electricity, an ion may be considered to be a compound of positive or negative electrons with the element in question. The formation of an ion is, then, entirely analogous to the formation of a compound from two ordinary elements. For instance, in the formation of ions from sodium iodide, the sodium atoms combine with positive and the iodine atoms with negative electrons. This conception is very comprehensive, for according to it, the law of electrochemical change, Faraday's law, appears as a consequence of the laws of definite and multiple proportion. Although the theory of electrolytic dissociation was not spared great opposition in its early years, it has successfully advanced until at the present time by far the greater number of investigators accept it and recognize its value. Quote, "It would be impossible to give in a few words a clear conception of all the reasons which led Arrhenius to adopt his now almost universally accepted views," unquote, says Langbein in his electrodeposition of metals. Quote, "And a short statement of these views must therefore suffice. He discovered that according to the degree of dilution and the nature of their combination, salts in aqueous solutions are to a more or less far-reaching extent decomposed into independent portions, that is, the ions, and the term electrolytic dissociation is applied to this phenomenon. Only combinations which dissociate are decomposed and thus form ions, can be conductors of the current, the progressive motion of the latter being solely taken care of and affected by the ions. The ions are supposed to be charged with a certain quantity of electricity, the cations with positive, the anions with negative electricity, and so long as current passes through to the electrolyte, they move free in the latter. However, when a current is conducted through the electrolyte, the ions are attracted by the electrodes, the positively charged cations by the negatively charged cathode, and the negatively charged anions by the positively charged anode. By reason of these movements of the ions to the electrodes, this phenomenon is called migration of the ions. The ions, on reaching the electrodes, are freed of their charge, that is, they yield their electricity to the electrodes. They lose thereby their ion nature, being transformed by their separation on the electrodes into the allotropic or isomeric form of the element or combination." Unquote. After the true action of Volta's pile had been discovered, the first modification was to immerse the plates of copper and zinc in the liquid. This arrangement gave a more powerful and lasting effect than the original pile. Volta arranged the cells in a circle and called such a battery a crown of cups. In 1806, the Royal Institution of London became possessed of a battery of 2,000 elements on the trough system. It was with this apparatus that Davy succeeded in decomposing potash and soda. This simple type of cell would, however, only work for a short time on account of the collection of bubbles of gas on the plates. That is, the cells became polarized. Becquerel studied this effect and succeeded in overcoming it to a great extent in 1829 by employing two different liquids separated by a porous partition, each of which enclosed one of the electrodes. In 1863, Professor Daniel invented the cell known by his name, and which is one of the most constant current cells ever made, although not so powerful as some. The zinc and copper electrodes are here separated by a jar of porous earthenware, the zinc being surrounded by dilute sulfuric acid, and the copper by a saturated solution of sulfate of copper. This latter solution is the depolarizer, acting to prevent the bubbles of hydrogen from collecting on the copper plate, as would be the case in the simple cell. Instead of hydrogen being thrown out at the copper pole, copper is deposited from the sulfate of copper depolarizer, so that this solution becomes constantly weaker and the copper heavier. To prevent the weakening, sulfate crystals are added occasionally. This battery has been much employed in telegraphic work. A form of this cell, known as the gravity cell, has been much used for this purpose, the porous partition having here been done away with, and the separation of the liquids affected by the difference in their densities. In 1839, Grove introduced a cell in which the depolarizer was strong nitric acid, which surrounded a platinum plate. This is a much more powerful depolarizer than sulfate of copper, and the cell was very energetic. It had, however, the disadvantage of high cost and gave off disagreeable fumes. The first drawback was overcome by Professor Bunsen in 1843, who substituted for the platinum plate one of gas retort carbon. The fumes, however, still remained. This battery was useful to the early experimenters, as it furnished a strong and constant current. Another good depolarizer is chromic acid. This is used in the same manner as nitric acid in the carbon-zinc cell of Bunsen. It does not, however, give off fumes, and yet is almost as powerful as the Bunsen cell. Various forms of this cell have been made, and they have been extensively used, especially for telephone work. They deteriorate only slightly on standing. Perhaps the most extensively used primary cell is the Leclance. This is also a zinc-carbon cell, but sal ammoniac is used to replace the sulfuric acid of the preceding cells, and the depolarizer is the black oxide of manganese. This depolarizer is slow in its action, and the cell is, therefore, not good for constant current work, but it has a very slow rate of deterioration. This cell is very extensively manufactured in the dry form, in which the exciting fluid is held as a moist paste. The cell is not entirely dry, however, as is sometimes supposed, for if it dries out, it ceases to work. One of the most recent primary cells, as well as the best, is the zinc-copper oxide cell of Lalande. In the Edison form of this cell, the copper oxide is pressed into plates and mounted in the cell between two zinc plates. The exciting fluid is caustic potash. The copper oxide acts as the depolarizer and is reduced to metallic copper. The cell is very efficient, has a long life, and does not deteriorate on standing. Thousands are now in use for such work as operating railway signals, sparking gas engines, etc. The existence of secondary currents was discovered by Ritter in 1803. Having substituted to the actions of a volta's pile another pile formed only of discs of copper, separated by moist cloth, he remarked that this second pile, though inactive by itself, gave in its turn an electric current in the opposite direction to the current of the first pile. This current was of but short duration, and the electromotive force was lower than that of the pile used in charging it. In 1826, de la Rive also found that a secondary or inverse current could be obtained from plates of platinum upon which oxygen and hydrogen had been disengaged in the experiment of the decomposition of water by a battery. This phenomenon took the name of polarization of the electrodes, and the current itself that of the current of polarization. After that, secondary currents were the object of many researches made by physicists, among whom many may be mentioned: Faraday, Grove, Wheatstone, Poggendorff, E. Becquerel, and Gauguin. In 1859, Gaston Plante studied the influence of different metals and different liquids on the production of secondary currents and on their intensity. Since that date, the question has assumed great importance, having received scientific and practical applications due mainly to the researches of this acute observer. He experimented on voltammeters with wires of copper, silver, tin, aluminum, iron, zinc, gold, and platinum, and for each of them varied the nature of the liquid into which the electrodes were placed. He found that, quote, all the metals oxidizing at the positive pole of the cell, the secondary current obtained after the interruption of the primary current was as much more intense as the oxidation was more complete, if the oxide form remained adherent and insoluble in the acidulated liquid of the voltammeter. Unquote. Even gold and silver did not resist the action of the oxygen of the pile. They were covered with dark deposits of oxide and furnished an energetic secondary current. Platinum did not oxidize, it is true, in a visible manner, but the secondary inverse current was of shorter duration than that of the metals which were covered with a layer of adherent oxide, an effect which was explained by the rapid decomposition of the oxygenated water produced around the positive electrode of the voltammeter. The action of the hydrogen was, on the other hand, stronger with platinum than with all the other metals, for the electrode around which this gas was disengaged furnished, with another neutral electrode, a more intense secondary current than when any other metal was employed. The most important result of these interesting researches is that which assigns the greatest intensity to the secondary current produced by a voltammeter with electrodes of lead and dilute sulfuric acid as the liquid. Measuring the electromotive force developed in such a voltammeter after the rupture of the primary current, Plante found it was equal to about 1.5 times, more exactly 1.48 to 1.49, that of the most energetic voltaic element, such as a Grove or Bunsen. This suggested the idea of constructing secondary cells and uniting them in a battery so as to store up or accumulate the work of the voltaic pile, in the same way that static electricity is condensed by the aid of conductors of great surface separated by an insulating material. The action in a storage cell is as follows. When the battery is charged, the positive plate consists of lead peroxide and the negative of pure lead in a spongy condition. When the cell discharges, both plates become a form of lead sulfate. Upon being charged by having a reverse current sent through them, they are reformed into lead peroxide and sponge lead. If the plates were platinum, oxygen would be given off where the current enters and hydrogen where it leaves. But with the lead sulfate plates, the oxygen and hydrogen combine, thus oxidizing one and reducing the other. Storage cells have many uses. They are employed in large sizes in central power stations to equalize the load on the machinery, serving to help the engines carry the maximum loads so that they are not strained. Electric automobiles are largely used, but the weight of the battery seriously handicaps their other excellent qualities. They also find application in lighting trains, operating industrial locomotives, supplying telephone lines, and igniting gas engines. End of section 25. Electricity, Chapter 7.
Section 26. The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 8. The Telephone, Part 1. In 1854, a Frenchman, Charles Bourseul, predicted the transmission of speech and outlined a method, correct save in one particular, but for which error one following his directions could have produced a speaking telephone. His words at this date seem almost prophetic. I have asked myself, for example, if the spoken word itself could not be transmitted by electricity. In a word, if what was spoken in Vienna may not be heard in Paris. The thing is practicable in this way. Suppose that a man speaks near a movable disk, sufficiently flexible to lose none of the vibrations of the voice. That this disk alternately makes and breaks the connection from a battery. You may have at a distance another disk which will simultaneously execute the same vibrations. The words makes and breaks in Bourseul's quotation have been italicized by the present writer. They form the keynote of the failures of those who subsequently followed Bourseul's directions literally. Philip Reis, a German inventor, constructed what he called a telephone in 1861, following implicitly the path outlined by Bourseul. He mounted a flexible diaphragm over an opening in a wooden box, and on the center of the diaphragm fastened a small piece of platinum. Near this he mounted a heavy brass spring with which the platinum alternately made and broke contact when the diaphragm was caused to vibrate. These contact points formed the terminals of a circuit containing a battery and the receiving instrument. His receiver assumed various forms, prominent among which was a knitting needle wrapped with silk-insulated copper wire and mounted on a cigar box for a sounding board. Its operation was as follows. The sound waves set up in the air struck against the diaphragm of the transmitter, causing it to vibrate in unison with them. This caused the alternate making and breaking of the circuit at the point of contact between the platinum and the spring, and allowed intermittent currents to flow through the receiver. These caused a series of sounds in the knitting needle by virtue of Page's effect. The sounding board vibrated in unison with the molecular vibrations of the needle, and the sound was thus greatly amplified. Reis's telephone could be depended upon to transmit only musical sounds. The question as to whether it actually did transmit speech has been the subject of much discussion. But if it did this at all, it was very imperfectly. The cause of its failure, says K.B. Miller in his American Telephone Practice, to successfully transmit speech will be understood from the following facts. A simple musical tone is caused by vibrations of very simple forms, while sound waves produced by the voice in speaking are very complex in their nature. Sound possesses three qualities: pitch, depending entirely on the frequency of the vibrations, loudness, depending on the amplitude of the vibrations, and timbre, or quality, depending on the form of the vibration. The tones of a flute and a violin may be the same as to pitch and loudness, yet be radically different. This difference is in timbre, or quality. Reis's transmitter, as he adjusted it, was able only to make and break the circuit, and a movement of the diaphragm barely sufficient to break the circuit produced the same effect as a much greater movement. The current therefore flowed with full strength until the circuit was broken, when it stopped entirely. The intermediate strengths needed for reproducing the delicate modulations of the voice were entirely lacking. This apparatus could therefore exactly reproduce the pitch of a sound, but not its timbre and relative loudness. For the next 15 years, no apparent advance was made in the art of telephony, although several inventors gave it their attention. In 1876, Professor Alexander Graham Bell and Professor Elisha Gray almost simultaneously invented successful speaking telephones. Gray has been one of the principal claimants for the honor of being the first inventor of the telephone, but Bell has apparently established his right to it and has also reaped the profit, for after long litigation, the United States Patent Office and the courts have awarded the priority to him as against Gray and many others. Bell possessed a greater knowledge of acoustics than of electrical science, and it was probably this that led him to appreciate wherein others had failed. His instrument consisted of a permanent bar magnet, having on one end a coil of fine wire. In front of the pole carrying the coil, a thin diaphragm of soft iron was so mounted as to allow its free vibration close to the pole. 2 points will be noticed, says Miller, in the work before cited, which have heretofore been absent: that no battery is used in the circuit, and that the transmitting and receiving instruments are exactly alike. When the soft iron diaphragm of the transmitting instrument is spoken to, it vibrates in exact accordance with the sound waves striking against it. The movement of the diaphragm causes changes in the magnetic field in which lies the coil, which changes, as already pointed out, cause currents to flow in the circuit. These currents flow first in one direction and then in the other, varying in unison with movements of the diaphragm, the waves being very complex as represented graphically. Passing along the line wire, these electrical impulses, so feeble that only the most delicate instruments can detect them, alternately increase and decrease the strength of the permanent magnet of the receiving instrument, and thereby cause it to exert a varying pull on its soft iron diaphragm, which as a result takes up the vibrations and reproduces the sound faithfully. Bell's earlier instruments were exhibited in 1876 at the Centennial in Philadelphia. The receiver consisted of a tubular magnet composed of a coil of wire surrounding a core and enclosed in an iron tube, which was about 1/4 inches in diameter and 3 inches long. This tube was closed by a thin iron armature or diaphragm which rested loosely on the upper face of the iron tube, the length of the core being such as not quite to touch the diaphragm when in this position. The whole of it was mounted on a base, arrangements being made to adjust the air gap between the pole of the core and the diaphragm by means of a thumb screw. The transmitter consisted of an electromagnet in front of the core, on which was adjustably mounted a diaphragm of gold beater's skin carrying a small iron armature at its center. A long mouthpiece, into which the sounds to be transmitted were spoken, served to convey the sound waves more directly to the diaphragm. Nearly all books and articles on telephones, says Miller, that treat of Bell's earlier receiver at all show and describe it as having the diaphragm fastened at one edge by a single small screw to the upper face of the iron tube, and sprung away from the tube at its opposite side. This mistake occurred in the first 2 editions of this work, and would have been in this one, but for Thomas D. Lockwood, who was kind enough to call attention to it. The origin of the error is explained in the following interesting extract from a letter written by Mr. Lockwood to the writer of this book. This mistake first appeared in the account given by Engineering of Sir William Thomson's address to the British Association in September 1876, and has been universally copied. The origin of the mistake is very odd. The screw of the instrument given to Sir William Thomson, and which he exhibited in England on his return, was put through a hole in the edge of the diaphragm and engaged with the threaded hole of the tube, for the purpose of attaching the diaphragm while in transit to prevent it from getting lost. No one, however, notified Sir William of this, it probably having been forgotten. And Sir William seems to have forgotten what the instrument as he saw it in Philadelphia looked like. Finally, in knocking about among Sir William's luggage, the free end of the diaphragm was apparently, and without doubt unintentionally, bent upward, as the picture shows. But when so bent, being at the same time rigidly fastened at the opposite edge, it would not and could not work, and when Sir William showed it in England, he couldn't make it work. Bell's instrument in a modified form is the standard of today. It is now used as a receiver only, a more efficient transmitter depending upon entirely different principles having been invented. In speaking of Bell's invention, Sir William Thomson, Lord Kelvin, said, "Who can but admire the hardihood of invention which devised such very slight means to realize the mathematical conception that if electricity is to convey all the delicacies of quality which distinguish articulate speech, the strength of its current must vary continuously as nearly as may be in simple proportion to the velocity of a particle of air engaged in constituting the sound." Much has been said and books have been written on the rights of Rees as the inventor of the speaking telephone. The validity of Bell's controlling patent was the subject of many attacks, the litigation finally reaching the Supreme Court of the United States. In the opinion of this court, October term 1887, the following brief but comprehensive statement is found. "We have not had our attention called to a single item of evidence which tends in any way to show that Rees or any one who wrote about him had in his mind that anything else than the intermittent current caused by the opening and closing of the circuit could be used to do what was wanted. No one seems to have thought that there could be another way. All recognized the fact that the minor differences in the original vibrations had not been satisfactorily reproduced, but they attributed it to the imperfect mechanism of the apparatus used, rather than to any fault in the principle on which the operation was to depend. It was left for Bell to discover that the failure was due not to workmanship, but to the principle which was adopted as the basis of what had to be done. He found that what he called the intermittent current, one caused by alternately opening and closing the circuit, could not be made under any circumstances to reproduce the delicate forms of the air vibrations caused by the human voice in articulate speech, but that the true way was to operate on an unbroken current by increasing and diminishing its intensity. Such was his discovery, and it was new. Rees never thought of it, and he failed to transmit speech telegraphically. Bell did, and he succeeded. Under such circumstances, it is impossible to hold that what Rees did was an anticipation of the discovery of Bell. To follow Rees is to fail, but to follow Bell is to succeed. The difference between the two is just the difference between failure and success. A very interesting fact, and one which might have changed the entire commercial status of the telephone industry, is that in 1868, Royal E. House of Binghamton, New York, invented and patented an electrophonetic telegraph, which was capable of operating as a magnetotelephone in the same manner as the instruments subsequently devised by Bell. House knew nothing of its capabilities, however, unfortunately for him. The instrument is provided with a sounding diaphragm of pine wood stiffened with varnish, mounted in one end of a large sound-amplifying chamber, so formed as to focus the sound waves at a point near its mouth where the ear was to be placed to receive them. The electromagnet adapted to be connected in the line circuit had its armature connected by a rod with the center of the wooden diaphragm. By this means, any movements imparted to the armature by fluctuating currents in the line were transmitted to the diaphragm, causing it to give out corresponding sounds, and any movements imparted to the diaphragm by sound waves were transmitted to the armature, causing its movements to induce corresponding currents in the line. Two of these instruments connected in a circuit would act alternately as transmitters and receivers in the same manner as Bell's instruments. It has been shown that in order to transmit speech by electricity, it is necessary to cause an undulatory or alternating current to flow in the circuit over which the transmission is to be effected, and that the strength of this current at all times be in exact accordance with the vibratory movements of the body producing the sound. Bell's magnetic transmitter was used as the generator of this current, as a dynamo, in fact, the energy for driving which was derived from the sound waves set up by the voice. The amount of energy so derived was, however, necessarily very small, and the current correspondingly weak, and for this reason was not a practical form of transmitter except for comparatively short lines. Elisha Gray devised a transmitter which, instead of generating the undulatory current itself, depended for its action on causing variation in the strength of a current generated by some separate source. This variation in current strength always being in accordance with the movement of the diaphragm. He mounted on his horizontal vibrating diaphragm a metal needle extending into a fluid of low conductivity, such as water. The needle formed one terminal of the circuit, the other terminal being a metal pin extending up through the bottom of the containing vessel. The vibrations of the diaphragm was supposed to cause changes in the resistance of the path through the fluid, on account of the varying distance between the points of the electrodes and therefore corresponding changes in the strength of the current. Bell also used a liquid transmitter in which a conducting liquid was held in a conducting vessel, forming one terminal of the circuit. The other terminal was a short metallic needle carried on the diaphragm and projecting slightly into the liquid, so that the area of contact between the liquid and the needle would be varied to better advantage by the vibration of the diaphragm than if the needle were immersed a greater distance into the fluid. Bell's liquid transmitter depended on variation in the extent of immersion of the electrode, while Gray's instrument, owing to the great extent to which the pin was immersed, depended rather on the variation in the length of the conducting path through the liquid itself, a faulty principle for this purpose. Bell's liquid transmitter was also exhibited at the Philadelphia Centennial in 1876, and, unlike that of Reese, simply caused variations in the resistance of the circuit and thereby allowed a continuous but undulatory current to pass over the line, the variations in which were able to reproduce all the delicate shades of timbre, loudness, and pitch necessary in articulate speech. Gray and Bell embodied, or attempted to embody in these instruments, the main principle upon which all successful battery transmitters are based. A battery furnished the current, and the transmitter, actuated by the voice, served to modulate it. It was not long, however, before a much better means was devised for putting this principle into practice. End of section 26. Section 27. The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3. Edited by Francis Rolt Wheeler. Electricity. Chapter 8. The Telephone, Part 2. In 1877, Emil Berliner of Washington, D.C. filed a caveat, and later in the same year applied for a patent on a transmitter depending upon a principle pointed out in articles published in 1856, 1864, and 1874 by the French scientist Dumoncel, that if the pressure between two conducting bodies forming part of an electric circuit be increased, the resistance of the path between them will be diminished, and conversely, if the pressure between them be decreased, a corresponding increase of resistance will result. Berliner's transmitter is shown in principle in Figure 37, which is a reproduction of the principal figure in his now famous patent. In this, A is the vibratory diaphragm of metal, against the center of which rests the metal ball C, carried on a thumb screw B, which is mounted in the standard D. The pressure of the ball C against the plate A can be regulated by turning the thumb screw. The diaphragm and ball form the terminals, or electrodes of a circuit, including a battery and receiving instrument. The action of this instrument, which at best has never been satisfactory or commercial, is as follows. When the diaphragm vibrates, the pressure at the point of contact A becomes greater or less, thus varying the resistance of the contact and causing corresponding undulations in the current flowing. Soon after this, Edison devised an instrument using carbon as the medium for varying the resistance of the circuit with changes of pressure. Edison's first type of carbon transmitter consisted simply of a button of compressed plumbago, bearing against a small platinum disc, secured to the diaphragm. The plumbago button was held against the diaphragm by a spring, the tension of which could be adjusted by a thumbscrew. A form of Edison's transmitter devised by George M. Phelps in 1878 is shown in Figure 38. The transmitting device proper is shown in the small cut at the right of this figure, and is enclosed in a cup-shaped case formed of the two pieces A and B as shown. Secured to the front of the enlarged head of the adjustment screw, E, is a thin platinum disc, F, against which rests a cylindrical button G of compressed lamp black. A plate of glass, I, carrying a hemispherical button K, has attached to its rear face another platinum disc, H. This second platinum disc rests against the front face of the lamp black disc, G, and the button K, presses firmly against the center of the diaphragm, D. The plates F and H form the terminals of the transmitter, and as the diaphragm D vibrates, it causes variations in the pressure and corresponding changes in the resistance of the circuit, thus producing the desired undulations of current. Professor David B. Hughes made a most valuable contribution tending toward the perfection of the battery transmitter. By a series of interesting experiments, he demonstrated conclusively that a loose contact between the electrodes, no matter of what substance they are composed, is far preferable than a firm, strong current. The apparatus used in one of his earlier experiments, made in 1878, is shown in Figure 39 and consists simply of 3 wire nails, of which A and B form the terminals of the circuit, containing a battery and a receiving instrument. The circuit was